Have you ever noticed how completely still your life feels? You lie in bed at night, the room is quiet, the ceiling does not move, and your breathing settles into a slow, steady rhythm. Yet at that same moment, the ground under you is turning faster than a jet. The whole planet is racing around the sun, and the sun itself is plunging through the galaxy. You do not feel your bones leaning, your heartbeat does not stutter, your coffee mug does not slide off the table. It is as if the universe has hidden its speed from your senses on purpose. How can everything be spinning on every scale, while your own body feels so perfectly at rest? And if our calm is really built on layers of motion, what does that say about the true state of the universe we live in? Right now, as you listen, Earth is rotating once every 24 hours, which means that near the equator, the ground sweeps along at roughly 1,000 miles per hour. At the same time, our planet is circling the sun at about 67,000 miles per hour. Wrap that orbit into a larger spiral, and you find the solar system gliding around the center of the Milky Way at close to 500,000 miles per hour. Beyond that, the galaxy itself moves through a web of other galaxies, part of a vast flow we can barely visualize. You are carried by all of these motions at once, yet your inner world reports only stillness. How is that possible? To understand why you do not feel this cosmic ride, it helps to remember when you do feel motion. You notice the car when it accelerates away from a stoplight, not when it cruises steadily on a smooth highway. You feel a lift in your stomach when a plane takes off or hits turbulence, not when it glides quietly at cruising altitude. Your inner ear has tiny structures that sense changes in speed and direction, not constant motion. Our bodies evolved to respond to jolts, swerves, and sudden stops, because those are the kinds of changes that could throw us off balance or threaten our survival. Quiet, steady movement is almost invisible to our senses. Physics has a simple word for this resistance to changing motion: inertia. An object that is moving in a straight line at a constant speed keeps moving that way unless something pushes or pulls on it. An object at rest stays at rest unless something acts on it. The same rule applies to you, your chair, and your coffee. If everything in your local world shares the same smooth movement, there is no relative jolt to disturb that state. The coffee stays in the cup because the cup, the coffee, your hand, and the floor are all moving together along the same gentle path. As long as there is no sudden difference in their motion, there is nothing for your body to notice. You can feel how important differences are by stepping onto a spinning playground ride. When it begins to rotate, you are pushed outward, your feet strain to stay under you, and your stomach knows something has changed. That outward push is a sign that your body wants to continue in a straight line, while the floor under you keeps turning. The faster the rotation, the stronger that conflict becomes. Now compare that with Earth. Although our planet spins, its rotation is very smooth and very slow compared to the scale of our body. Gravity presses you firmly toward the ground, and the slight outward effect of rotation is tiny at human scale, so you do not feel any sideways tug. The turning is there, but its influence is woven so gently into the pull of gravity that your senses do not notice. Another key idea is that motion is always relative. There is no cosmic scoreboard that tells you whether you are truly moving or truly still. You can sit in a train carriage, look at another train gliding past in the opposite direction, and feel for a moment as if your own train is the one slipping backward. Inside a plane, you can toss a ball straight up and watch it fall back into your hand, even though the entire aircraft is moving hundreds of miles per hour relative to the ground. In each case, your body and your surroundings share the same overall motion, so from your point of view, everything nearby behaves as if it were at rest. The outside world may be rushing by, but your local frame of reference feels calm. Orbiting astronauts are a dramatic example of this shared motion. The International Space Station circles Earth roughly every 90 minutes, travelling at over 17,000 miles per hour. That speed sounds extreme, yet inside the station, the astronauts float weightless. Their tools drift beside them, and droplets of water hang in the air. They do not feel thrown backward or mashed into a wall. That is because they, the station, and everything inside it are all in the same state of continuous freefall around Earth. Their path curves because of gravity, but there is no floor holding them up, so there is no sensation of weight. To them, the violent speed is invisible, replaced by a gentle drifting stillness. Once you start thinking this way, you can see that what we call rest is often just shared motion. Your room is not a fixed stage that the universe moves around. It is more like a raft carried by several rivers at once, each flow adding its own direction and speed. Because you, your furniture and your walls all ride those rivers together, you hardly notice any current at all. This can feel unsettling. If there is no absolute rest and no master reference frame, then what does it even mean to say that something is really spinning? The answer lives in the subtle ways rotation leaves fingerprints on the world. For a long time, people suspected that Earth might be turning, but the motion felt so smooth that it was hard to prove. One of the most elegant demonstrations hangs quietly in some science museums. A long, heavy pendulum swings back and forth, tracing the same line through space again and again. At first, it seems as if nothing more is happening. Then you notice that the direction of the swing slowly drifts over the course of the day, as if an invisible hand were twisting the entire room. The secret is that the pendulum tries to keep its swinging plane fixed in space, while Earth rotates beneath it. As the planet turns, the floor, the ceiling, and the observing crowd rotate under the swinging weight, so the path appears to rotate. You are watching the difference between a local sense of stillness and the larger spin of the planet. Other clues are even more familiar. Day and night are a direct consequence of rotation. The sun appears to rise, cross the sky, and set. But we now know that this daily cycle is our own horizon turning into and out of the light. If Earth did not spin, one side would face the sun constantly, while the other remained in endless darkness. Instead, every point on the surface is swept through sunlight and shadow in a regular rhythm, warming and cooling, brightening and dimming. The very concept of a day is a measure of how long it takes our planet to complete a single turn. When you check a clock, you are coordinating your life with the slow spin of the ground beneath your feet, even if it feels like the ground never moves. Yet Earth does not rotate with perfect machine-like regularity. Over long periods, its spin gently changes. Tides raised by the moon drag on the oceans, which in turn tug on the planet and slowly steal a little of its angular momentum. The result is that days gradually lengthen over millions of years. Massive earthquakes and melting ice sheets can shift how mass is distributed inside and on the surface of Earth, which slightly adjusts the rotation rate. We are talking about tiny fractions of a second, spread over long spans of time, far too subtle for your heartbeat to notice, yet precise instruments can measure them. When scientists add a leap second to our official timekeeping, they are quietly acknowledging that the planet does not spin with perfect constancy. All of this means that the stillness you trust is not a deep cosmic truth. It is a clever illusion created by the fact that you and your environment share motion on many levels. Your senses tune out anything that is smooth, steady, and shared by everything around you. They light up only when there is a conflict, when one part of your world moves differently than another. In a way, your perception is a filter that hides the universe and shows you only what you need to navigate daily life. That makes sense for survival, but it also means that our intuitive picture of reality leaves out most of the grand choreography that is actually happening. Once you see that, an interesting soft challenge appears. Can you, in your imagination, learn to feel the hidden motion anyway? The next time you sit quietly in a chair, you might try to hold both truths at once. On one level, your muscles relax, your breath is calm, your surroundings feel rock solid. On another, you know that you are being carried in a slow spin around Earth's axis, around the sun, around the galaxy. You may even picture the stars above as not just distant lights, but as markers of the giant circle your planet traces in space. That mental shift is a kind of participation in the investigation. You become aware that your apparent still point is really part of a vast, shared journey. Thinking this way also raises a deeper question that our senses will never answer on their own. If constant motion can feel like rest, then how did all of this motion begin in the first place? At some point in the distant past, the matter that would become our planet, our sun, and our galaxy must have acquired its spin. The fact that it feels so ordinary today does not make its origin any less mysterious. When you follow the chain of motion backward in time, you eventually run out of familiar explanations. The collapsing cloud that formed the solar system had to be turning already. The galaxy that cloud belonged to had to be rotating. The early universe had to contain some pattern that allowed rotation to exist at all. In other words, the quiet turning you do not feel is not just a local curiosity. It is a clue that points all the way back to the beginning of time. Every steady orbit, every hidden spin, every calm room that drifts through space without a tremor is part of a story that started long before Earth cooled or life emerged. If you accept that your own stillness is only a shared, uniform motion, then the natural next step is to ask where that motion came from. Somewhere in the early universe, something set the stage so that nothing could remain perfectly, absolutely still. And that is the trail we now need to follow, back toward the first moment when the cosmos itself began to turn. If we want to understand where all this hidden motion came from, we have to do something strange in our minds. We have to run the universe backward. Imagine time as a film reel and start rewinding. Galaxies draw inward instead of flying apart. Stars unburn their fuel and collapse into uniform gas. Planets dissolve back into disks of dust. The further back you go, the smoother and hotter everything becomes, until the entire observable universe shrinks into a dense, bright fog of particles and light. In that early fireball, there are no planets, no galaxies, no pendulums, not even atoms as we know them. Yet somehow, buried in that chaos, is the recipe for every rotation that exists today. Cosmologists give names to those early stages, even though we cannot see them directly. At the very beginning, there is the Planck era, a time so close to the start that space, time, and energy behave in ways we still do not fully understand. Our best theories break down under those conditions. Immediately after that, the universe goes through an unimaginably rapid expansion known as inflation. In a tiny fraction of a second, space itself swells by a colossal factor, stretching any initial irregularities to cosmic scales. When inflation slows down, the universe is filled with hot plasma, a mixture of particles and light, almost perfectly uniform, but not quite. Those small imperfections are crucial. Even in that early plasma, there are places that are a little denser and places that are a little emptier. You can think of them as tiny hills and valleys in the distribution of matter and energy. Without them, everything would remain smooth forever. No clumps, no clouds, no stars. With them, gravity has something to work with. The slightly denser spots pull in more material, grow heavier, and attract even more. Over millions of years, these seeds will grow into galaxies. The question for us is whether those first tiny differences can also plant the seeds of rotation. One way to picture this is to imagine rain falling into a still pond. If the drops are perfectly symmetric, everything spreads out evenly with no swirl. But if the drops fall in a slightly uneven pattern, the water starts to organize itself into gentle eddies and currents. Gravity does something similar on cosmic scales. When nearby regions of space have slightly different densities, the gravitational tugs from different directions do not quite cancel. Over time, those mismatched pulls twist collapsing clouds of gas. The result is angular momentum, the measure of how much something is rotating. Once a cloud starts to spin, that spin is very hard to get rid of completely. We see the outcome of that process all across the universe today. Many galaxies are giant rotating disks. Stars form in swirling clouds. Planets condense from spinning protoplanetary disks that orbit young stars. The same basic story repeats on different scales. Gravity pulls, small asymmetries give a gentle twist, and conservation of angular momentum keeps that twist alive as things shrink. A collapsing cloud that starts with a tiny, almost invisible rotation can end up as a rapidly spinning object once it has shrunk by a huge factor. This is why figure skaters spin faster when they pull in their arms. They are conserving angular momentum in a very human-sized demonstration of a galactic rule. But there is an even deeper question hiding under this story. We can explain how small initial patterns get amplified into the spins we see, but where did those initial patterns come from? Why was the early universe not perfectly smooth in the first place? The leading idea is that quantum fluctuations, the tiny jitters required by quantum physics, were stretched to cosmic size during inflation. At the smallest scales, empty space is never truly empty. Fields fluctuate, particles pop in and out of existence, and energy densities flicker. When inflation blows those microscopic jitters up to astronomical size, they become the slight over and under densities that gravity then amplifies. This is not just an elegant story on paper. We have a fossil record of those early ripples. It is called the cosmic microwave background. About 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral atoms. At that moment, light that had been constantly scattered by free charges suddenly began to travel freely through space. That ancient light has been streaming ever since, stretched by the expansion of the universe into microwave wavelengths. When we map its temperature across the sky, we see tiny variations. Some spots are a little warmer, some a little cooler, by only a few parts in 100,000. Those temperature spots correspond to the early density ripples. Slightly denser regions ended up slightly cooler in that snapshot, while slightly emptier regions ended up slightly warmer. The pattern looks like random noise at first glance, but it carries a wealth of information. By analysing the size, strength, and distribution of these fluctuations, scientists can infer how the early universe behaved, how much matter it contained, and how inflation might have worked. For our story, those maps show us the seeds from which later structure and rotation grew. If you squint, you can almost see future galaxies and clusters hidden in that mottled sky. Some researchers have gone even further and asked whether the entire universe might have a preferred axis of rotation. When you look at the microwave background in detail, you can find certain large-scale alignments that seem to point in particular directions. One of these patterns has been nicknamed the axis of evil, not because it is truly sinister, but because it looks surprisingly coherent in a place where you might expect pure randomness. A few features in the data seem to line up with each other and with our local motion through the universe. That raises the provocative idea that space itself might be slightly anisotropic, that the cosmic fabric could have a faint built-in orientation. If the entire cosmos had a global spin, it would leave subtle fingerprints. Light coming from different directions could be affected in slightly different ways. The large-scale distribution of galaxies might show a faint swirl. Polarization patterns in the cosmic microwave background could twist in characteristic ways. Observations so far place strong limits on how much net rotation the universe can have. If there is a global spin, it must be extremely small. Still, just the possibility that the universe as a whole could have an overall sense of direction is enough to make us pause. It suggests that rotation might not only be a local byproduct of collapsing clouds, but could be written into the cosmos at birth. Whether or not there is a single cosmic spin axis, there is no doubt that rotation is everywhere once structure forms. Early galaxies did not emerge as perfect static spheres. Simulations and observations both show that as matter flowed into growing halos, it brought angular momentum with it. Streams of gas and dark matter fell along cosmic filaments, the vast strands that connect clusters of galaxies. The geometry of those flows naturally imparted spin. As that matter cooled and settled, rotating disks of stars and gas appeared. In this sense, every spiral galaxy you see in a telescope is a fossil, not only of gravity at work, but of the precise way early matter came together. On smaller scales, even fundamental particles carry a kind of spin. In quantum mechanics, spin is not literally a tiny ball rotating in space, but it behaves in many ways like angular momentum. Electrons, protons, and many other particles have intrinsic spin that influences how they align in magnetic fields, how they combine to form atoms, and how they obey statistics in large groups. This intrinsic spin is built into our most basic description of nature. When you hold a magnet or study how materials conduct electricity, you are already dealing with the consequences of quantum spin. It is a reminder that the idea of rotation penetrates physics at every level, from galaxies to the smallest constituents of matter. There is a subtle, soft question hidden there that is easy to overlook. If spin is such a fundamental property of particles, does it have any connection to the larger scale rotations of stars and galaxies? Or are these just two separate uses of the same word? We do not yet have a complete theory that ties them together in a simple, satisfying way. Still, the fact that angular momentum appears both as an intrinsic quantum property and as a global feature of cosmic structures hints that rotation is not just an accident. It may be a deep feature of how our universe organizes itself. If you step back, you can see a theme emerging. The universe does not like perfect balance. Inflation magnifies tiny quantum jitters into real density differences. Gravity amplifies those differences into clumps. Those clumps rarely collapse straight inward. Tidal forces and asymmetric infall give them a little twist, and conservation of angular momentum protects that twist as they shrink. At the quantum level, particles insist on carrying spin even when they are point, like in our models. Everywhere you look, motion gets locked into rotational patterns rather than fading away. Order appears, not as a static crystal, but as dynamic, persistent turning. This is where our earlier question about your apparently still room deepens into something more profound. When you feel at rest, you are not only sharing the motion of Earth, the Sun, and the galaxy, you are also resting inside a universe that, from its earliest moments, has been biased toward rotation on many levels. Your sense of calm is built on structures that only exist because early fluctuations were amplified into spins. If those early density ripples had been different, if inflation had left a smoother cosmos, if gravity had not turned unevenness into swirling collapse, your everyday experience of stillness might never have existed at all, because there might have been no planets, no stars, perhaps no long-lived structures where life could arise. So when we ask who or what set the universe turning, we are really asking about the origin of those first asymmetries and the laws that turned them into lasting motion. Was the pattern fixed by the rules of quantum fields and general relativity, with no further explanation needed? Did inflation have specific properties that favoured certain kinds of fluctuations? Are there deeper principles that determine how much angular momentum appears on different scales? These questions sit at the frontier of cosmology. We do not yet have clean, final answers, but we have enough clues to trace how the early fireball evolved into a rotating cosmos. The next natural step is to follow that rotation down into the environments we actually know well. It is one thing to speak of galaxies spinning in distant darkness. It is another to realize that the length of your day, the climate that surrounds you, and the stability of the world you walk through are all direct consequences of Earth's rotation. If cosmic events long ago set the universe turning, then they also indirectly set the tempo of your own life. To see how, we have to bring the story down from the scale of microwave backgrounds and inflation to the more familiar, but still remarkable, spinning sphere that you call home. When you picture Earth in space, you might see a blue marble hanging quietly in the dark, a kind of cosmic ornament. In reality, that marble is spinning, and that simple fact shapes almost everything about the world you experience. If Earth did not rotate, or if it spun very differently, the planet under your feet would be almost unrecognizable. The length of a day, the way air and water move, the patterns of weather, even the internal workings of the core are all tied to the planet's turn. To understand how a universe that learned to rotate built a world where life could take hold, you and I need to look closely at what a spinning planet actually does. Start with the most obvious gift of rotation, day and night. Because Earth turns, different parts of the surface take turns facing the sun. No point on the planet is locked in eternal daylight or endless darkness. Instead, there is a rhythm. Light arrives, warms the ground, drives photosynthesis, and then fades into night as the surface cools and the sky fills with stars. That daily cycle sets the tempo for biological clocks. Plants open and close their leaves, animals wake and sleep. Your own body temperature, hormone levels, and alertness rise and fall with this spin-driven pattern, even when you think you are ignoring it. If Earth did not rotate, one side would face the sun almost constantly, while the other would be trapped in perpetual night. The day side could heat to searing temperatures, while the night side would plunge into deep cold. Somewhere in between, along a permanent twilight band, conditions might be more moderate, but the gentle sweeping of sunlight that you take for granted would vanish. Instead of a planet bathed in a slow, global breathing of light and darkness, you would have a world split into a scorched face and a frozen shadow. It is possible that life could adapt to such extremes, but it would be a very different story than the one we live. Earth's rotation does more than turn the lights on and off. It also nudges the way air and water move. Because the planet spins, different latitudes move at different speeds. The equator covers more distance in a day than regions closer to the poles. As air flows north or south, it passes through zones that are moving faster or slower beneath it. That mismatch bends the path of winds and currents, a phenomenon often called the Coriolis effect. Instead of simple straight-line flows from hot to cold, you get swirling patterns, jet streams, storm systems, and great ocean gyres that redistribute heat around the globe. You can think of rotation as adding a twist to the planet's attempt to smooth out temperature differences. Warm air rising near the equator and cooler air sinking at higher latitudes would create a simple two-cell circulation in a world that does not rotate. On a spinning Earth, those flows break into multiple bands, each with its own prevailing winds and characteristic weather. The same is true for the oceans. The spinning Earth helps organise currents like the Gulf Stream, which carries warm water toward higher latitudes and moderates climates that would otherwise be much colder. The climates that support forests, grasslands and cities all ride on this rotating engine. Even deep inside the planet, rotation leaves its mark. Beneath your feet lies a layered interior, a solid inner core, a liquid outer core, a viscous mantle, and a rigid crust. The outer core is made of molten metal that moves and churns. As that conductive fluid flows, it generates Earth's magnetic field through a process known as the geodynamo. Rotation helps organise those flows, guiding the motion of the liquid metal so that a large-scale, stable magnetic field can emerge, rather than a chaotic tangle of fields that cancel each other out. The result is a magnetic shield that deflects charged particles from the Sun and cosmic rays from deep space. Without that magnetic shield, the upper atmosphere would be far more exposed. Solar wind could strip away lighter gases over long timescales, as it did on Mars. High-energy particles could bombard the surface more intensely, making conditions harsher for life, especially on land. When you watch a compass needle settle toward north, you are seeing a quiet, everyday reminder that the core is moving, and that the planet is rotating in a way that sustains a protective bubble around you. That field nests your daily life inside an invisible safety zone carved out of a very active space environment. To appreciate how rotation and internal motion work together to make Earth habitable, it helps to compare our world with its neighbours. Take Mars. It has a day length similar to ours, only slightly longer, and it does rotate. Yet today, Mars has a thin atmosphere, a cold surface, and only a weak remnant of a global magnetic field. Evidence suggests that it once had a thicker atmosphere and flowing water. Over time, its smaller size allowed its interior to cool more quickly. The core lost much of its convective motion. As the internal dynamo faded, the global magnetic field weakened. Solar wind, no longer deflected as strongly, could strip the Martian atmosphere more efficiently. Rotation alone was not enough to save it. Venus offers a different contrast. It is similar to Earth in size, but its rotation is slow and unusual. A Venusian day is longer than its year, and the planet spins in the opposite direction compared to most other worlds in the solar system. Because of that slow spin, the day-night cycle on Venus is very long. The atmosphere is thick, dense, and filled with carbon dioxide, with clouds of sulfuric acid. The surface bakes under an intense greenhouse effect. The slow rotation means that the Coriolis effect plays out differently. Circulation patterns and atmospheric dynamics there are not simple copies of Earth's. Again, we see that the rate and direction of spin help shape climate and environment. These comparisons are not just trivia. They show that there is a delicate interplay between rotation, internal structure, atmosphere, and incoming energy from the Sun. A planet with Earth's distance from its star but with a very different spin could land in a very different climatic regime. Too slow a rotation, and you risk extreme dayside heating and nightside cooling. Too fast, and you could have violent winds and complex weather patterns that might leave little room for stable ecosystems. The balance we experience is not guaranteed. It is one outcome among many possibilities consistent with the same laws of physics. On our world, life has woven itself around the specific rhythm that rotation provides. Organisms from bacteria to humans carry internal clocks known as circadian rhythms. These biological timers run on cycles close to one Earth day. They regulate sleep and wakefulness, feeding, cell repair, and many other processes. Even when isolated from external cues like sunlight, many organisms keep ticking on roughly this 24-hour cycle for a time. Over millions of years, evolution has tuned the machinery of life to the tempo set by the planet's spin. Change that tempo significantly, and biology would need to adapt or fail. Tides are another way that rotation interacts with gravity to shape our world. The Moon's gravity pulls more strongly on the side of Earth that faces it and less strongly on the far side. This difference creates bulges in the oceans. As Earth rotates under these bulges, coastlines move in and out of deeper water, leading to the regular rise and fall of sea levels that we call tides. The Sun adds its own tidal influence, sometimes amplifying and sometimes moderating the lunar tides. Coastal ecosystems, many marine species, and even human activities like fishing and shipping organize around these rhythms. Again, rotation takes a gravitational effect and turns it into a repeating pattern that life can adapt to and use. The interaction between tides and rotation also feeds back into the long-term evolution of the Earth-Moon system. Tidal friction gradually transfers angular momentum from Earth's spin to the Moon's orbit. That is why the day lengthens over geological time, and why the Moon slowly recedes from the planet. If you could watch a time-lapse of Earth over billions of years, you would see its spin slowly winding down and the Moon spiralling outward. The present balance is a snapshot in a much longer dance. Yet it is in this particular era, with this length of day and this distance to the Moon, that complex life and human civilization emerged. Our growing catalogue of exoplanets has turned these ideas from speculative thought experiments into urgent questions. Astronomers have found many planets orbiting close to their stars, where tidal forces are strong. Some of those worlds may be tidally locked, always showing the same face to their star, much like the Moon always shows the same face to Earth. On such planets, one hemisphere would scorch under permanent daylight, while the other would freeze in endless night, unless winds and ocean currents distribute energy efficiently. Models suggest that some tidally locked planets could still host habitable regions near the boundary between light and dark, but the global picture of habitability there is tightly linked to how the planet's rotation and orbit interact. There are also planets that spin extremely rapidly, or have tilted axes that create wild seasonal swings. Each configuration tells us something about how diverse the conditions for life might be. When researchers simulate climates on such worlds, they consistently find that rotation rate, axis tilt, and orbital distance form a three-way partnership that determines where liquid water can exist and how stable environments might be. Earth, with its specific spin and tilt, sits in a sweet spot that allows broad regions of relatively mild conditions over long spans of time. That stability gives evolution room to explore complexity. As you think about this, there is a quiet but powerful soft realization. Your sense of normal weather, of familiar seasons, of the length of your days is not just a local quirk. It is the outcome of cosmic history. The same processes that seeded rotation in collapsing clouds and galaxies eventually set the spin of this planet, which in turn shaped the envelope in which life could arise. When you walk outside and feel a breeze, you are feeling the subtle consequence of air deflected by a spinning world. When you feel yourself getting sleepy at night, your internal clock is obeying the same 24-hour beat that the planet has been keeping for eons. This also nudges us toward a more fragile view of our comfort. If small changes in rotation rate, axis tilt, or internal dynamics could produce a very different kind of Earth, then the world we inhabit is not guaranteed to last in its current form forever. Over very long timescales, the day will continue to lengthen, the continents will rearrange, the balance of ice, ocean, and atmosphere will shift. Some changes will be driven by internal processes, others by the steady evolution of the Sun. Spin is not a fixed backdrop, it is a slowly changing parameter in a complex system that happens to be stable enough right now for us to reflect on it. So far, we have treated rotation as a kind of stage manager for climate, magnetism, and biological rhythm. But there is another layer to the story, one that takes us back to the deeper structure of reality. When a massive object spins, it does not only move through spacetime, it also affects spacetime itself. At gentle levels, that influence is subtle, almost impossible to notice in daily life. Push rotation to extremes, however, and the fabric of time and space begins to twist. Clocks tick at different rates, paths of light bend in unexpected ways. The same quiet turning that gives you day and night can, in more extreme forms, start to bend time. And that is where our investigation is heading next. People first heard that gravity is not just a force but a bending of spacetime. It sounded abstract, almost poetic. Yet that idea becomes very concrete once you let things spin. In Einstein's picture, mass and energy tell spacetime how to curve, and spacetime tells matter how to move. If you add rotation, the story gains another layer. A rotating mass does not just sit in a static dimple of spacetime. It stirs the fabric, twists it, and drags nearby paths along with its spin. Time itself, which you might imagine as a straight river flowing past, starts to swirl. We already know from special relativity that motion changes the way time passes. A clock that moves fast with respect to you will tick more slowly in your frame than a clock that stays at rest beside you. General relativity adds that clocks deeper in a gravitational field also run slower than clocks higher up. These effects are not guesses. They have been measured by comparing precise atomic clocks flown on airplanes with clocks left on the ground, and by watching how time passes on satellites orbiting Earth. When you combine high speed and strong gravity, the difference between one clock and another can become dramatic. Rotation brings these relativistic ideas into a new regime. When a massive object spins, it not only curves spacetime, but also drags it around. This effect is called frame dragging. One way to picture it is to imagine a heavy ball spinning in thick honey. The honey near the surface is pulled along, swirling as the ball turns, and that swirl extends outward. In a similar way, spacetime near a rotating mass is not quite stationary. It is gently twisted, and anything nearby, even light itself, must adjust its path to that rotating geometry. Around Earth, the frame dragging effect is incredibly small. If you tried to feel it directly, you would fail. But it is not zero, and careful experiments have managed to catch it in the act. One of the most delicate was a mission called Gravity Probe B. Engineers placed ultra-precise gyroscopes in a satellite and let them spin freely while orbiting Earth. In the absence of any external influence, the axis of each gyroscope should have pointed in a fixed direction in space. Over time, scientists measured tiny drifts in those axes, consistent with the predictions of general relativity. Part of that drift came from the way Earth's mass curves spacetime. Another part came from frame dragging, the subtle twisting of spacetime by the planet's rotation. It is humbling to realize that your relatively ordinary world quietly sits in a slightly stirred spacetime. Earth is not massive or compact enough to produce wild relativistic effects. Yet even here, where life feels Newtonian and predictable, there is a faint swirl imprinted on the fabric of time and space. If you let your imagination follow that swirl outward and ask what would happen around an object that spins far faster or packs far more mass into a small volume, the quiet ideas of relativity turn into something almost shocking. The same rules that barely nudge a gyroscope in low Earth orbit can dominate the behaviour of entire stars. Neutron stars are one of the clearest examples. They are the collapsed cores of massive stars that exploded as supernovae. Imagine an object with more mass than the Sun squeezed into a sphere only about 20 kilometers across. Many neutron stars spin incredibly rapidly, some rotating dozens or even hundreds of times per second. Their magnetic fields are intense, and as they spin, they sweep beams of radiation through space like cosmic lighthouses. We call those that point their beams across Earth pulsars, because we detect them as regular pulses of radio waves or X-rays. Near such a rapidly spinning compact object, space-time is deeply curved and strongly twisted. If you could hover close to the surface, your clock would tick significantly slower than a clock far away in interstellar space. The pulses themselves carry a record of this warping, As the radiation climbs out of the neutron star's gravitational well, its frequency is shifted. This gravitational redshift is a sign that time is running differently near the star than it is for you. Precise timing of pulsars allows astronomers to test general relativity in regimes where both strong gravity and rapid rotation matter. Yet even neutron stars are only a stepping stone to the most extreme rotators we know about. Black holes push the idea of rotation to its logical limit. A non-rotating black hole already bends spacetime so severely that nothing, not even light, can escape from within a certain boundary called the event horizon. Add spin, and the geometry becomes even stranger. The solution that describes a rotating black hole is called a Kerr geometry. In that spacetime, there is a region outside the event horizon called the ergosphere, where the frame dragging is so strong that no object can remain at rest relative to distant stars. Everything is forced to co-rotate in some sense. Inside the ergosphere, space-time itself is dragged around so fiercely that every path forward has a rotational component. If you tried to hover motionless above a spinning black hole within that region, no amount of rocket thrust could keep you fixed in place relative to the distant universe. Your efforts would simply change how you spiral, not whether you spiral. Time and space have traded some of their roles. Directions that used to be purely spatial now mix with time in ways that are hard to visualize. The very notion of standing still with respect to the wider cosmos breaks down. We cannot visit these regions directly, but we can observe their influence on matter and light. Many black holes, especially the supermassive ones at the centers of galaxies, are surrounded by accretion disks. Gas spirals inward, heating up as it falls, and emits radiation, often in X-rays. The inner parts of these disks orbit at relativistic speeds, close to the speed of light. Their photons must climb out of a deep gravitational well and escape from a region of intense frame dragging. The result is that the spectra we measure, the timing of flares, and the shape of certain emission lines carry the fingerprint of both strong gravity and rotation. By modelling those signatures, astronomers can estimate how fast a black hole is spinning. A rapidly rotating black hole can drag the inner edge of its accretion disk closer in than a non-rotating one could. That changes the maximum temperature of the disk and the pattern of radiation. In some systems, we observe echoes of X-ray flashes reflected off different parts of the disk at slightly different times. Those time delays and distortions reveal how space-time is warped and twisted near the event horizon. In this way, rotation, which you first met as the gentle turning of Earth under a pendulum, becomes a key parameter in decoding some of the most violent regions in the universe. All of this might sound remote from your daily life, but rotation, bending time, is not only a distant phenomenon. The technology you rely on every day already has to account for relativistic effects that involve both motion and gravity. Consider the Global Positioning System, the network of satellites that allows your phone to know where you are. Each satellite carries atomic clocks that broadcast time signals. Your device calculates its position by comparing the arrival times of those signals from multiple satellites. For this to work, the clocks must stay synchronized to within billionths of a second. However, those clocks are not sitting on Earth's surface. They orbit higher up, where gravity is slightly weaker, and they move at high speed relative to the ground. General relativity predicts that clocks in weaker gravity run a bit faster than those deeper in a gravitational well. Special relativity predicts that moving clocks run a bit slower than stationary ones. In the case of GPS satellites, the gravitational effect wins, so the satellite clocks naturally run faster than ground-based clocks would. Engineers have to correct for this difference. If they did not, the timing errors would accumulate, and your calculated position would drift by many meters each day. In other words, the map app you casually consult is quietly relying on Einstein's description of time. Earth's rotation enters the story in several ways. The planet is not a perfect sphere. Because of its spin, it bulges at the equator, which changes the exact shape of its gravitational field. That shape affects how clocks tick at different latitudes and altitudes. The rotation also means that by the time a signal has travelled from a satellite to a receiver on the ground, the receiver has moved slightly. The system has to account for these shifts. What feels to you like a simple dot on a screen following your walk is underneath a delicate dance between spinning satellites, a rotating Earth, and a relativistic spacetime in which time is not uniform. Even the instruments that sense rotation directly, used in aircraft and ships, are often based on relativistic principles. Ring laser gyroscopes and fiber optic gyroscopes exploit what is called the Sagnac effect. They send beams of light in opposite directions around a closed loop. If the device rotates, the effective path length for one beam changes relative to the other, leading to an interference pattern that reveals the rotation rate. This is closely connected to the way motion and the structure of spacetime affect how light propagates. Once again, a principle firmly rooted in relativity ends up providing very practical information about how something is turning. If you step back from these details, a pattern emerges. Rotation and time are intertwined at every level. A spinning mass stirs spacetime, and that stirred spacetime dictates how clocks tick and how objects move. At modest scales, the effect is tiny and easy to overlook. At extreme scales, near neutron stars and black holes, it dominates the scene. On Earth, you experience a tame version of these effects as slightly shifting clock rates and tiny drifts in gyroscopes. Across the universe, the same principles shape accretion disks, jet directions, and the timing of signals we detect from distant sources. There is a quiet, personal implication hidden in this cosmic picture. Your own experience of time is anchored to a network of clocks that are constantly being adjusted, corrected, and aligned with a rotating planet under a curved sky. When you set an alarm or check the time on your phone, you are trusting a chain of technology and theory that links your wrist to the motion of satellites and the rotation of Earth itself. The tick of your second is not a pure, independent tempo. It is synchronized with a world in motion and with a universe where rotation and gravity conspire to make time a flexible quantity. All of this pulls us toward a deeper question that goes beyond any single experiment or device. If rotations bend time and help set the pace of events, then the pattern of spins on every scale acts like a kind of cosmic clockwork. There are atomic clocks, planetary days, stellar rotations, and galactic spinning disks, all ticking at their own rates, all influenced by gravity and angular momentum. Who or what sets these rates? How did the universe decide how fast each of these gears should turn? And once they are turning, how do they trade motion and time among themselves over billions of years? When we talk about cosmic clockwork, it is tempting to imagine some hidden metronome outside the universe, a master tick that tells every planet, star, and galaxy how fast to turn. In reality, there is no such external timekeeper. Instead, the universe sets its own tempo from the inside out, starting from the smallest scales and building upward. If you want to see who controls the rates of rotation that bend time and shape worlds, you have to follow the trail from atoms to planets to galaxies, and notice how each level hands motion to the next without any overseer. At the foundation of our modern timekeeping is a very specific atomic vibration. The official second is defined using cesium atoms. When a cesium atom flips between two particular energy states, it emits radiation at a frequency that is extraordinarily stable. The second is now defined as the time it takes for that radiation to oscillate exactly 9,192,631,770 times. This is not poetry, it is the literal heartbeat of our global clocks. That micro-world transition, grounded in quantum spin and energy levels, sets the pace for your phone, your computer, and international time standards. Before atomic clocks, the second was tied directly to Earth itself. It was defined as 1/86,400th of the mean solar day, the average time between successive noons as Earth rotates under the Sun. That made intuitive sense. People have lived by the rising and setting of the Sun for as long as there have been people. But as measurements grew more precise, it became clear that Earth does not spin like a perfect, unchanging flywheel. Its rotation wobbles and drifts. Days are not identical. Atomic clocks, which tick with remarkable uniformity, began to outpace the planet that had inspired them. This mismatch forces us to face an odd fact. Our most precise measure of time is now anchored to the quantum behavior of cesium, while our lived experience of time is still anchored to the turning of Earth. To keep civil time in step with the planet, Timekeepers occasionally add a leap second to coordinated universal time. When that happens, clocks in data centers, observatories, and navigation systems are told to count 61 seconds in a particular minute. Nothing about the cesium atoms has changed. Instead, we are sliding our human definition of time a tiny bit so that noon stays roughly aligned with the sun overhead. It is a small reminder that Earth's spin is not under our control. Why does the planet's rotation drift at all? One of the main reasons is tidal friction. The moon's gravity pulls on Earth's oceans, raising bulges in the water. Because Earth rotates, those bulges are carried a little ahead of the line directly beneath the moon. The gravitational tug between the offset bulges and the moon transfers angular momentum from Earth's spin to the moon's orbit. Earth slowly loses rotational energy and its day lengthens. The moon gains orbital energy and moves farther away. This is not a story about a steady, eternal clock. It is a slow, ongoing trade in angular momentum between two partners locked in a gravitational embrace. Over very long timescales, continents moving, ice sheets melting, and mass shifting within the mantle also change how matter is distributed on Earth. That alters the planet's moment of inertia, its resistance to changes in rotation. When mass moves closer to the axis, the planet can spin a bit faster. When mass moves outward, the spin slows. It is the same principle you see when a spinning skater extends or withdraws their arms. Our world constantly adjusts its spin in response to internal rearrangements and external tugs. No hidden hand is turning a dial. The rules of conservation and the actual flows of matter decide the outcome. If we step out from Earth to the solar system, we see similar logic playing out on a grander scale. Our sun and planets formed from a collapsing cloud of gas and dust in the young galaxy. That cloud did not have perfect symmetry. It had a slight net rotation, and as it contracted under its own gravity, its spin rate increased. To conserve angular momentum, the cloud flattened into a disk. Most of the mass collected in the center to form the sun. The rest stayed in the disk, where clumps grew into planets, moons, asteroids, and comets. Each object inherited some of the original angular momentum, distributed according to the detailed way matter clumped and collided. The direction in which planets orbit the sun, and the way most of them rotate on their axes, reflect this shared origin. They are all participating in the same rough sense of spin that the original nebula had. But their individual rotation rates and axial tilts are not all the same. That variety is largely due to violent events in the early solar system. Giant impacts, close encounters, and the steady accretion of smaller bodies all redistributed angular momentum. Uranus, with its axis tilted almost onto its side, is a dramatic example. Its strange orientation is likely the fossil of a colossal collision long ago. There was no cosmic engineer designing these spins. There were initial conditions, physical laws, and a lot of time for interactions to play out. Even now, long after the chaos of formation, the solar system continues to shuffle angular momentum among its members. Tides between moons and planets can slowly change rotation rates and orbital periods. Mercury is locked in a spin-orbit resonance with the Sun, rotating 3 times for every 2 orbits. That state is the result of tidal interactions and energy dissipation over vast spans of time. Resonances between planets and asteroids carve gaps in the asteroid belt. The dance is ongoing. The familiar periods you learn in school, like the length of Earth's year or the orbit of Jupiter, are not timeless constants. They are current values in a system that is still evolving. Zoom out further to the galactic scale, and the same question of who sets the rotation appears again, now painted in starlight. The Milky Way spins as a result of the way its matter, both visible and dark, collapsed and clumped in the early universe. Streams of gas flowed along cosmic filaments into emerging halos, bringing angular momentum with them. As those halos grew and cooled, disks formed and stars lit up within. There is no external wheel turning the galaxy. Its spin is the memory of how matter fell together and the ongoing result of gravitational interactions between stars, gas clouds, and the huge, unseen halo of dark matter that surrounds everything. Underlying all of this is a remarkable rule. In the absence of external torque, the total angular momentum of a system is conserved. That is more than just a convenient pattern. It is tied to a deep symmetry in the laws of physics. If the laws look the same when you rotate your point of view, then angular momentum has to be conserved. In other words, the fact that there is no preferred rotational orientation built into the laws themselves leads directly to the persistence of spin. Once any part of the universe starts rotating, it will keep rotating, or pass that rotation on to other things, unless a force actively redirects it. This conservation law does not tell the universe how much angular momentum to have in the first place. It simply says that whatever amount exists in a closed system will be preserved, shifting from one form to another. A spinning cloud can extend its edges into a disk. A binary star can lose orbital angular momentum as it emits radiation, and compact objects spiral together. A planet can slow its spin as it transfers angular momentum to a moon. The total keeps its books balanced, even as the details change. If you could freeze the universe at one moment and tally all the spins, then step ahead and tally again, the grand total would be the same, even though individual objects might be moving very differently. In practice, no system is completely isolated. Friction, radiation, tides, and outflows all connect one object to another. Angular momentum flows along those channels. A newly formed star can shed rotational energy through stellar winds, or by launching jets along its magnetic field lines. A black hole accreting matter can transfer some of its spin to escaping radiation and jets, slowly changing its rotation rate. At every step, the bookkeeping still holds. The angular momentum does not vanish, it just migrates. What looks like a choice about how fast something spins is, at a deeper level, the result of all the past trades and interactions that brought it to that state. Your own sense of time sits on top of this layered, evolving structure. The second on your watch is defined by atomic transitions. The cycle of your day is set by Earth's rotation. The calendar you follow is based on Earth's orbit around the Sun. The precession of Earth's axis, the gravitational pull of other planets, and the slow changes in the Sun's output all tug on these rhythms. Yet when you look at a clock or a calendar, you see clean numbers and regular grids. Human culture has wrapped the messy, shifting motions of the cosmos in a simple system of hours, days, and years, as if the universe were a perfect machine. There is a quiet invitation hidden in that contrast. You can choose to see time as a rigid schedule handed down from above, or you can see it as a set of conventions anchored to ongoing, imperfect motions. The leap second that appears every so often is a small signal that we are adjusting our conventions to keep up with the physics, not the other way around. If the Earth-Moon system continues to evolve, if the day lengthens and the lunar month grows, future civilizations may need different conventions. Our definitions are practical tools built on top of a deeper, restless clockwork that owes its existence to angular momentum and gravity. So when we ask who controls the cosmic clockwork, the answer that emerges from physics is not a who at all. It is a combination of symmetries, conservation laws, and initial conditions. The universe does not decide how fast to spin on each scale. It simply follows rules that preserve certain quantities while allowing energy and motion to flow. Those rules do not care about our preference for neat cycles or round numbers. They do not guarantee that any given world will have a gentle day-night rhythm or a long-term stable climate. They only guarantee that once motion exists, it will be shepherded along consistent lines. That answer, while powerful, does not quite close the story. It pushes the mystery back one level. If conservation of angular momentum and the symmetries behind it shape how rotation behaves, why does the universe have those symmetries at all? Why is it that turning your perspective leaves the laws unchanged, while reversing time or swapping matter for antimatter does not always do the same? Somewhere in those slight asymmetries lies the reason that the universe did not remain in perfect balance, but instead began to move, clump, and rotate in the first place. To understand why any clock can tick or any planet can spin, we have to examine how perfect symmetry might fail, and why that failure is exactly what allows time and motion to exist at all. Imagine for a moment a universe that is perfectly balanced. Matter and antimatter are present in identical amounts. Every direction in space looks exactly the same. Every region has the same density and temperature. Nothing is a little heavier or a little lighter than anything else. In that kind of flawless symmetry, there is no reason for anything to change. No preferred way to fall, no seed for a clump, no tilt that might turn into a spin. It would be a frozen, featureless perfection. Beautiful as an idea, and completely sterile. You can see a simpler version of this in everyday life. Balance a pencil perfectly on its tip, and in theory, it could stay that way forever. In practice, any tiny disturbance decides which way it falls. The upright state is symmetric. There is no preferred direction. Once it picks a side, the symmetry is broken. The same is true when water freezes into ice crystals. The liquid has no preferred direction at the molecular level. As it cools, particular patterns form, and that uniform symmetry gives way to specific shapes. It is in that act of choosing, of breaking symmetry, that structure appears. Physics takes this idea very seriously. Many of our most powerful theories start from the assumption that the laws themselves are symmetric under certain transformations. Rotate your point of view, and the equations stay the same. Shift everything in time or space, and the rules do not change. At very high energies, it seems that even the fundamental forces may have been unified, described by a more symmetric set of laws than the ones we see today. As the universe expanded and cooled, those symmetries did not remain manifest. They broke in stages, like a series of phase transitions, and each break introduced new distinctions and new possibilities. In the early universe, when everything was unimaginably hot and dense, the forces we now call electromagnetism and the weak nuclear force behaved as a single electro-weak interaction. As cooling progressed, that unified force split. The symmetry that had tied them together broke. A field that had been hovering at a high, symmetric value slid into a new configuration. That slide is closely connected with the Higgs field acquiring a non-zero value throughout space. Particles that had moved as if they were massless suddenly gained mass through their interaction with this field. The universe went from a state where motion and forces had one character to a state where they had another. This was not a neat and gentle rearrangement. When a symmetry breaks, different regions can make different choices about the exact pattern they adopt. Think of a crowd of people, each deciding which way to face when a starting gun goes off. At first, there is confusion, then clusters emerge. In the early universe, these choices and mismatches left imprints. Some ideas about topological defects and relics from these transitions have been largely ruled out, but the general lesson remains. The move from high symmetry to lower symmetry is how the cosmos generated richness from simplicity. The tiny ripples we see in the cosmic microwave background are one expression of that process. They are the record of small differences in density and temperature frozen into the universe when it was still young. Those differences arose from quantum fluctuations stretched by inflation and filtered through the behavior of matter and radiation as the plasma cooled. If the early universe had been exactly the same everywhere, those ripples would not exist. Without ripples, gravity would have nothing to amplify into galaxies and clusters. Rotation would have no foothold because nothing would clump and twist. Broken symmetry is what allowed those first seeds of structure and later spin to appear. There is another, sharper imbalance built into our world. Look around and you see matter. Stars, planets, dust, people. You do not see equal amounts of antimatter. If the Big Bang had created matter and antimatter in exactly equal quantities and treated them in exactly symmetric ways, every particle of matter would have found a partner and annihilated into light. The universe would be left with radiation and little else. Yet here we are, in a cosmos dominated by matter, with antimatter appearing only in trace amounts in cosmic rays and high-energy processes. Somewhere in the early universe, that balance was tipped. To explain this, physicists look for mechanisms of baryogenesis, processes that can generate an excess of matter over antimatter. Certain conditions must be met. Reactions must violate conservation of baryon number in a controlled way. they must occur out of thermal equilibrium, and they must treat matter and antimatter slightly differently. That last requirement is known as violation of charge parity symmetry, often shortened to CP violation. In everyday language, it means the laws must distinguish between a process and its mirror image, with particles swapped for antiparticles. We do see CP violation in nature. Experiments with particles called kaons and B mesons have shown that some decays, when viewed in a mirror and with matter swapped for antimatter, do not behave exactly the same. The probabilities tilt ever so slightly. That tilt is tiny, but it proves that the universe does not respect perfect symmetry between matter and antimatter. It has a preference, a bias, even if it is a subtle one. The puzzle is that the CP violation we have measured so far may not be enough, by itself, to explain the large matter excess we observe. So the search continues, in colliders and underground laboratories, for deeper sources of asymmetry. You might notice a pattern here. The universe begins in a simple, nearly symmetric state. As it cools, symmetries break, forces differentiate, fields slide into new configurations, tiny biases emerge in the behavior of matter and antimatter. Those small departures from perfect balance are amplified by cosmic expansion and gravity into the structures we see today. Without them, no galaxies, no stars, no planets, no chemistry, no life. Imperfection is not a flaw on the surface of a basically perfect universe. It is the engine that makes anything interesting possible. Symmetry breaking also threads through our understanding of time itself. On paper, many of the fundamental equations look almost the same if you run them forward or backward. Replace t with minus t in a simple Newtonian problem and you can trace a motion in reverse. In practice, your experience of time has a clear direction. Eggs break, but pieces do not leap off the floor and assemble into eggs. Heat flows from hot coffee into the cooler air, not the other way around. This directional flow is tied to entropy, the tendency of systems to move from special ordered states to more probable, disordered ones. For entropy to increase over time, the universe had to start in an incredibly special, low entropy state. That requirement itself is a kind of asymmetry. The early cosmos was hot and dense, yet extremely smooth in its gravitational degrees of freedom. Over time, gravity turned that smoothness into clumps, stars, black holes, and large-scale structures, increasing gravitational entropy. Our thermodynamic arrow of time points from that special past toward a more disordered future. Again, a perfect balance, a perfectly random high-entropy beginning, would not have allowed this story to unfold. The very fact that time feels like it flows depends on a fundamental imbalance in initial conditions. On a more microscopic level, the laws of physics are not completely symmetric under time reversal either. Once you factor in CP violation and connect it with deeper symmetries, you find that reversing time changes certain processes in ways that matter. The combined symmetries of charge, parity, and time together, known as CPT, seem to be preserved. But individually, C, P, and T are not. The result is that our universe carries built-in arrows. It has a preferred way for certain reactions to proceed. It has an initial low entropy state that defines a temporal direction. These slight tilts are enough to turn a timeless set of equations into a world where you remember the past and anticipate the future. Rotation is quietly entangled with these asymmetries. Consider parity symmetry, the idea that the laws of physics should not care whether you are living in a left-handed or right-handed coordinate system. For a long time, this felt obviously true. Then experiments in the mid-20th century showed that the weak nuclear force violates parity in a dramatic way. Neutrinos, the ghostly particles that stream through your body by the trillions every second, are produced only with one-handedness. Their spins are always aligned in a particular way relative to their motion. Nature, at a fundamental level, prefers left over right in this context. That preference is a kind of built-in handedness or chirality in the laws of physics. It might seem far removed from the spirals of galaxies or the rotations of planets, but it points to a deeper principle. The universe is not indifferent to orientation at every scale. It contains genuine preferences. In chemistry and biology, chirality appears again. Many molecules exist in mirror image forms, like left and right hands. In a purely symmetric world, you would expect life to use both forms equally. Instead, the amino acids that build proteins in your body are almost all of one-handedness, and the sugars in DNA and RNA are of the opposite handedness. Life has chosen a side. The origin of this biological homochirality is still an open question. Some hypotheses involve slight energetic differences between mirror image molecules. Others look to polarized light from distant stars, asymmetric reactions on mineral surfaces, or even the influence of parity-violating forces at a very small level. Whatever the detailed mechanism, the result is that the chemistry of living systems has a preferred orientation. Your body, down to its molecular machinery, expresses a broken symmetry that echoes deeper asymmetries in the laws governing particles. You can think of this cascade as a chain of choices. At the top, the early universe chooses, through symmetry breaking, to differentiate forces and give particles mass. A tiny imbalance favours matter over antimatter. A low entropy initial condition gives time a direction. At smaller scales, certain interactions prefer left over right. Molecules learn to favour one-handedness. Life builds on that choice. Somewhere in the middle, gravity grabs the density ripples and spins them into galaxies, stars and planets. Rotational motion on cosmic scales and the chiral structures inside your cells are different chapters in the same story of how symmetry fails just enough to let complexity bloom. There is a soft but important realization tied to our original question about motion and spin. If the universe had been perfectly symmetric in all ways, rotation as we know it might never have existed. Without density ripples, no clumps. Without clumps, no collapsing clouds. Without slight imbalances in flows, no net angular momentum. The clocks we use, the days we live by, the orbits that carry planets around stars, all depend on layers of broken symmetry that started in the first fractions of a second after the Big Bang. Every spinning world and every turning galaxy is a kind of fossil of that original decision to leave perfection behind. At this point, you might be wondering whether we have accounted for all the ingredients that actually shape the spins we see. We have talked about visible matter, forces we know, and fields we can model. Yet when astronomers measure how fast many galaxies rotate, they find a problem. Based only on the gravity of the stars and gas we can see, those galaxies should tear themselves apart. The outer regions orbit too quickly. Something unseen must be providing additional gravitational glue, an invisible mass that deepens the potential wells and anchors the spinning disks. This mysterious component, which we call dark matter, seems to be the hidden scaffolding that organizes much of the rotation in the universe. It does not glow or absorb light. It interacts very weakly, if at all, with ordinary matter through anything but gravity. And yet it dominates the mass budget of galaxies and clusters. If we want a complete picture of why the cosmos spins the way it does, and why galaxies hold together instead of flying to pieces, we have to step into this invisible architecture and ask what kind of shadowy substance is quietly controlling so much of the cosmic dance. When astronomers first tried to weigh galaxies carefully, they expected a simple story. You measure how bright the stars are, estimate how much mass that light represents, add in gas and dust, then compare that mass with how fast those stars orbit. The faster something moves in a circle, the stronger the inward pull must be to hold it in place. In a spiral galaxy, stars near the centre feel the combined gravity of most of the mass inside their orbits, while stars farther out should feel less. Based on visible matter alone, you would expect the outer stars to move more slowly, just as planets far from the Sun orbit more gently than ones closer in. That is not what the data showed. In the 1900s, Fritz Zwicky studied the motions of galaxies in the Coma cluster and found that they were moving too fast to be held together by the visible mass alone. He proposed that some unseen substance, which he called dark matter, must be providing extra gravity. Decades later, Vera Rubin and her collaborators measured the rotation curves of spiral galaxies, plotting orbital speed against distance from the centre. Instead of dropping off at large radii, these curves flattened. Stars in the outer regions were orbiting almost as fast as those much closer in. something was adding gravitational glue in the outskirts. The simplest explanation is that each galaxy sits inside a much larger halo of invisible mass. The luminous disk of stars and gas is just the bright core of a much more massive, extended structure. The dark matter halo does not collapse into a thin disk because it does not cool and radiate energy the way gas does. It stays puffy and roughly spherical, reaching far beyond the visible edges. When you include such a halo in your calculations, the flat rotation curves make sense. The orbital speeds you observe are exactly what you would expect if most of the mass is hidden. Over time, the evidence for this invisible component piled up. In galaxy clusters, the motions of galaxies, the hot X-ray emitting gas between them, and the way the cluster bends background light all point to far more mass than stars alone can provide. This bending of light, known as gravitational lensing, is particularly compelling. Massive objects distort spacetime so strongly that they can magnify and shear the images of more distant galaxies behind them. By mapping these distortions, astronomers can reconstruct where the mass is, regardless of whether it shines. Again and again, they find that most of the mass sits in extended, smooth halos that outweigh luminous matter by a large factor. One of the most striking pieces of evidence comes from collisions between galaxy clusters. In systems like the so-called bullet cluster, two clusters have passed through each other. The hot gas clouds collided and slowed down, heating up and emitting X-rays. The galaxies, being mostly empty space, sailed through relatively unimpeded. When researchers mapped the mass using gravitational lensing, they found that most of it is centered on the galaxy distributions, not on the slowed gas. That matches the idea that dark matter barely interacts except through gravity. It goes where the galaxies go and does not pile up with the gas. From the perspective of rotation, dark matter is the invisible architecture that sets the stage. Without halos, many galaxies would simply not hold together. Their outer parts would fly off into space. With halos, the gravitational potential wells are deep enough that stars and gas can orbit stably at the speeds we observe. The pattern of spins we see in the sky is not just a story about visible disks. It is the visible tip of a much larger, invisible structure that quietly dictates which orbits are possible and which are not. On even larger scales, dark matter seems to trace out a cosmic web. Computer simulations that include dark matter, gas, and the known laws of physics start from early fluctuations similar to those seen in the cosmic microwave background. As they evolve, the dark matter clumps into filaments and nodes. Galaxies form along these filaments like bright beads on invisible threads. Where filaments intersect, massive clusters appear. The overall pattern of this simulated web matches what large sky surveys actually find when they map the distribution of galaxies. In this picture, dark matter halos form first, creating the gravitational wells into which normal matter later falls to form stars and spinning disks. You can imagine dark matter as the scaffolding of cosmic rotation. When a halo forms, it acquires angular momentum from the uneven flows of matter and the tidal torques of neighbouring structures. That angular momentum is stored in the dark component as well as in the gas and stars. As gas cools and sinks toward the centre, it settles into rotating structures that align with the overall spin of the halo. The graceful spiral patterns you see in a telescope are like luminous frost tracing out the underlying whirl of something you cannot see. Despite all this gravitational evidence, dark matter remains elusive at the particle level. It does not emit light, absorb it, or scatter it in any obvious way. It passes through ordinary matter with almost no direct interaction. That makes it hard to detect in laboratories. Many leading hypotheses propose that dark matter is made of new kinds of particles that interact through gravity and perhaps a feeble additional force, but not through electromagnetism. Experiments deep underground, shielded from cosmic rays, watch for rare collisions between these hypothetical particles and atomic nuclei. So far, hints have appeared and faded, and no decisive detection has been confirmed. Other approaches look for dark matter in the sky. If dark matter particles can annihilate each other under some conditions, they might produce high-energy photons or other particles as byproducts. Telescopes scan the centers of galaxies, the halos of clusters, and diffuse backgrounds for excess emissions that could be a signature. Again, there are tantalizing excesses in some datasets, but none have yet passed the strict tests needed to be called a discovery. The cosmos behaves as if dark matter is there, but the individual actors refuse to step into the spotlight. There are alternatives to the idea of dark matter as a substance. Some researchers have proposed that our understanding of gravity itself breaks down at low accelerations or large scales. In these modified gravity models, the laws governing motion in weak fields are slightly different from those in strong fields. The altered rules can, in some cases, reproduce flat rotation curves without invoking unseen mass. However, explaining the full range of observations, from galaxy scales to the cosmic microwave background, has proven challenging. While work continues, the simplest, most unifying picture still involves a new form of matter that gravitates but otherwise hides. For our story about motion and time, the exact identity of dark matter may matter less than its role in shaping where rotation can live. In a universe with only ordinary matter, the first galaxies would look different, form at different times, and perhaps be less stable. The delicate balance between centrifugal tendencies and gravitational binding would not work out the same way. The pattern of spins across billions of light-years would change. Dark matter is not just extra weight, it is a structural element that determines which rotating systems can survive and how they evolve. This realization adds another layer to your earlier sense of stillness. When you sit quietly and imagine Earth turning, the Sun orbiting the galactic center, and the galaxy drifting through the cosmic web, you are picturing motions that depend on dark matter halos you cannot perceive. Your entire solar system moves within such a halo, sharing its overall motion, feeling its gravity, but never touching it in any direct sensory way. The hidden mass sets the curvature of spacetime your world travels through and helps define the geometry of the orbit that feels so stable and enduring. There is a subtle participation you can attempt here if you like. You might imagine not just the visible stars arcing their way around the Milky Way, but a vast, unseen cloud of dark matter that extends far beyond them, enveloping your orbit. The Sun and its planets are like a small family riding inside a giant, transparent gyroscope whose axes you cannot see. The security you feel in the regularity of seasons and years is, in part, a trust in that invisible gyroscope. Without it, the shapes and speeds of orbits would change. Rotation would have a different character, and the long calm we have enjoyed might be harder to find. Dark matter also affects how angular momentum is shuffled over cosmic timescales. As galaxies merge and interact, their halos overlap and interpenetrate. The dark matter does not collide and shock the way gas does. Instead, it streams through, its particles feeling only gravity. As these halos blend, their angular momenta combine and redistribute. The shapes of the resulting galaxies, whether they end up as smooth ellipticals or disc-like spirals, depend on how these invisible components share their spin. The visible morphologies we classify so carefully are surface expressions of much deeper, darker dynamics. In some simulations, you can watch two spiral galaxies merge. Their disks tangle and warp, stars are flung into long tidal tails, and central bulges grow. Both galaxies plunge through each other multiple times before finally settling into a new configuration. The dark matter halos, though unseen, are the reservoirs that absorb much of the orbital angular momentum. They puff up, change shape, and help the system relax into a stable state. Without that extra degree of freedom, the outcome of such mergers would be different. Once again, the invisible component is not a minor detail. It is a key player in how motion is stored and rearranged. There is a quiet irony in all of this. The universe we see, with its luminous stars and glowing gas, is only a small fraction of what is actually there. Yet our intuitions about motion, stability, and rotation are built almost entirely on that visible fraction. We imagine planets circling stars and stars circling galaxies, but we rarely picture the larger halos and webs that anchor those paths. The more we learn, the more it seems that the rules of motion we experience depend on an unseen majority. Your daily stillness, your planet's orbit, and your galaxy's spin are all entangled with a dark background that refuses to light up. That entanglement raises a final, lingering question. If so much of the universe's angular momentum is stored in forms we cannot see, what will happen to all of this motion as cosmic time stretches on? Galaxies collide and merge, halos grow and blend, orbits change, radiation carries away energy, black holes swallow matter and spin it into their own rotations. At the same time, the expansion of the universe continues, stretching distances and thinning interactions. Somewhere between these processes lies the long-term fate of rotation itself. Will the cosmos keep turning in recognizable patterns forever? Or will its spins be diluted into a kind of quiet, almost motionless geometry? That is the path we are about to follow. To follow that path, we have to stretch our sense of time far beyond human history, far beyond even the age of Earth. On the scale of billions of years, the motions that feel eternal to us turn out to be temporary arrangements. The orbits of stars in our galaxy, the spins of planets, the rotations of galaxies themselves, are all chapters in a longer story. Angular momentum is conserved, but the way it is stored can change dramatically. The question is not whether motion disappears, but whether it remains organized in ways that matter for structure, energy, and life. On timescales that are almost comfortable by cosmic standards, the first big change is already written in our sky. Our galaxy and the neighbouring Andromeda galaxy are on a slow collision course. They are set to meet in a few billion years. As their dark matter halos overlap and their disks interpenetrate, their stars will not smash together like cars on a highway. Instead, gravity will weave their orbits into new patterns. The graceful spiral arms we see today will be shredded, flung into long tails, and eventually relaxed into a more rounded shape. During that process, the angular momentum that now lives in the ordered rotation of two separate disks will be redistributed. Some will end up in the orbits of individual stars flung into extended halos. Some will be absorbed by the dark matter, puffing it further. Some will be stored in the spin of a larger central concentration, perhaps a merged supermassive black hole. The final remnant may look like a single, massive elliptical galaxy, its stars moving in more random orbits rather than circling in neat, flat rings. The original pattern of rotation has not vanished, it has been scrambled. Zoom out and you see that this is not unique. Galaxies collide and merge throughout the universe. Over time, clusters grow, small systems are consumed by larger ones, and the delicate disks that carry so many spiral patterns give way to rounder, more relaxed forms. Mergers are one of the main engines that transform ordered rotation into more chaotic motion. The universe takes the clean spins you see in young disks and slowly stirs them, like a whirlpool stacking small eddies into larger, slower currents. Even on these scales, structure is slowly trading sharp rotation for a softer, more diffuse movement. At the same time, stars themselves evolve. Large stars burn through their fuel quickly and end their lives in supernova explosions, often leaving behind compact remnants such as white dwarfs, neutron stars, or black holes. These remnants are, in many ways, the densest storage units for angular momentum. A star that rotated modestly when it was large can spin very rapidly once its core collapses. Over eons, as gas is used up and locked into these remnants, more and more of the universe's organized spin ends up in extremely compact objects. The cosmic dance of rotation migrates inward. When two compact objects orbit each other, their motion does not stay fixed forever either. As they circle, they emit gravitational waves, ripples in spacetime that carry away energy and angular momentum. The orbit shrinks, the partners spiral closer, and eventually they merge. We have already detected some of these mergers through the faint shudder they send through the fabric of spacetime. Each event is a small step in the long process of turning orbital motion into radiation. Angular momentum is not destroyed, but some of it ends up imprinted in the spin of the final remnant, and some in the pattern of waves that wash outward into an ever larger, ever thinner universe. In the far future, after many such mergers, the universe will be more sparsely populated by bright, long-lived stars and more dominated by dark remnants. White dwarfs will cool and fade into black dwarfs. Neutron stars will slow as they radiate energy and interact with their environments. black holes will continue to swallow matter, and in doing so, adjust their own spin rates. On very long timescales, even black holes are not permanent. Quantum effects at the event horizon allow them to emit radiation, a process known as Hawking radiation. As they radiate, they lose mass and angular momentum, shrinking slowly. For stellar mass black holes, this evaporation is so slow that it is effectively irrelevant on any timescale we can truly imagine. But in the remote future, when most other sources of light are gone, Hawking radiation becomes the last whisper of ordinary matter and energy leaving these compact objects. As black holes shrink, their spins bleed away into a bath of low-energy photons and other particles. The universe's angular momentum budget is still conserved, but its storage mode has changed again. What was once the ordered rotation of galaxies and stars has become the faint polarization and direction content of a very dilute radiation field. Alongside these processes, the large-scale expansion of the universe continues. Unless something reverses or dramatically alters that expansion, distant galaxies will drift beyond each other's horizons. Regions that are not gravitationally bound will no longer be able to interact or exchange light. Each bound structure, such as a merged galaxy cluster, will become an island universe, evolving largely in isolation. Within each island, the redistribution of angular momentum will go on for a long time. Between islands, almost nothing will pass. The grand, connected web of cosmic structure will fade into scattered, lonely oases. Eventually, if current understanding holds, even those oases will quiet down. With no fresh gas to form new stars, with most matter locked in compact remnants, with black holes slowly evaporating, the universe trends toward a condition sometimes called heat death. In that state, matter and energy are spread so thinly and uniformly that there are no large gradients left to drive complex change. Locally, particles still move, angular momentum is still present in principle, but almost all of it is stored in extremely diffuse, low-energy motions that no longer build or sustain intricate structures. In a sense, this is the final act of symmetry breaking and its long aftermath. The early universe started in a special, low-entropy state that allowed structure and rotation to form and grow. Over time, those structures interacted, merged, radiated, and shared their motion. Entropy increased as energy was spread over more degrees of freedom. The memory of the original sharp patterns of spin faded. Heat death is not the absence of motion, it is the absence of useful differences, the loss of organized flows that can power stars, planets, or life. The universe becomes a place where, even though rotation technically persists, it no longer does work in the way we are used to. There are speculative possibilities beyond this picture. Some theories imagine that protons might ultimately decay, turning all matter into radiation over inconceivably long times. Others play with ideas of cyclic cosmologies, or new phases of physics that could change the story. But even within these variations, a recurring theme appears. Organized motion is temporary. The clear, structured rotations we rely on occupy a middle era. Before them, the universe was too hot and uniform to support lasting spin-based structures. After them, it becomes too sparse and smoothed out for those structures to survive. Seen from that perspective, your own moment in time is perched on a narrow ridge in cosmic history. You live in an epoch when galaxies are rich in stars, when planets can hold oceans, when day and night still mean something tangible. Rotation is not just an abstract property of distant systems. It is one of the main reasons your planet has a stable climate, a protective magnetic field, and a day length that life can synchronize with. The same angular momentum that once lived in density ripples and swirling gas clouds now sets the tempo of your mornings and nights. There is a quiet beauty in realizing that your heartbeat and thought patterns are built on these ancient motions. The iron in your blood was forged in the cores of stars that spun and orbited long before Earth existed. The elements that make up your body pass through collapsing clouds, rotating disks, and perhaps even supernova debris, before assembling into cells with their own chiral machinery. The fact that your biological clock runs close to a 24-hour cycle is a direct legacy of the planet's rotation. which itself was shaped by the way the solar system formed out of a spinning nebula. Even the way your mind experiences time has roots in this history. Your brain relies on ordered flows of ions, on rhythmic pulses, on cycles of activity and rest. Those rhythms evolved in an environment where the cycle of light and dark was stable, where seasons came and went in a predictable pattern, where gravity and rotation together provided a consistent stage. If the early universe had broken its symmetries differently, if the cosmic web had arranged its spins in another way, your own personal sense of before and after might never have come into being. Consciousness is not simply an emergent pattern in matter, it is an emergent pattern in matter that has lived inside a particular history of motion. You can participate in that realization simply by paying attention. The next time you watch the sun setting, you can hold two truths at once. On one level, it feels like the sun is dropping toward the horizon, painting the sky while you stand still. On another, you know that your planet is turning away from the star, that you are leaning into night as part of a global rotation. That rotation is part of a larger orbit around the galactic center. That orbit is embedded in a dark matter halo whose spin was set by ancient tides in the early universe. You are witnessing not just an evening, but a link in a chain of motion that stretches back to the first fractions of a second after the Big Bang. This awareness does not change the physics. The planet will keep turning whether you think about it or not, but it can change your sense of scale. The stillness you feel in a quiet room is no longer just an absence of movement. It becomes a carefully aligned frame of reference, a shared motion that hides its own speed. The ticking of your clock becomes a local approximation to a deeper set of rhythms that run from cesium atoms to Earth's spin to the rotations of galaxies and the whispered evaporation of black holes. In that light, the eventual fading of organized rotation is not only a story about loss, it is also a story about how improbable and precious the current era is. For a limited window, the universe supports planets with stable days, stars with long lifetimes, and chemistry that can explore complex possibilities. Within that window, life arises and, at least once that we know of, becomes aware enough to ask why anything spins at all. Your curiosity about motion is itself one of the universe's ways of reflecting on its own history of rotation. If you think back to the beginning of our exploration, we started with a simple question. How can everything be spinning on every scale while you feel so perfectly at rest? We followed that question outward into galaxies and dark matter halos, backward into the early universe, inward into the structure of time, and forward into a future where organized motion thins out. Along the way, we saw that stillness is an illusion created by shared movement, that rotation is one of the main ways the universe stores and transforms energy, and that broken symmetries in the first moments after the Big Bang seeded every spin you experience today. In the deep future, when galaxies have merged, when stars have gone dark, and when black holes have radiated away their mass and angular momentum, the universe may approach a quiet, nearly featureless state. In that state, there will be no new planets turning under warm suns, no complex climates, no living beings watching the sky. The grand patterns of rotation that once shaped everything will survive only as faint traces in a thin fog of radiation and a gently curved spacetime. The cosmos will have spent its store of low-entropy structure and settled into a kind of enduring, silent memory. Yet even in that imagined quiet, the history of motion will not be erased. It will be encoded in the distribution of energy, in the subtle correlations of fields, in the very shape of the geometry that remains. And in our era, before that distant evening arrives, part of that memory lives in you. Every time you feel the pull of gravity, every time you watch a storm spiral on a weather map, every time you count the passing of a day, you are participating in the vast, ongoing story of a universe that learned to turn. For a while, you get to witness it. For a while, you are the part of the cosmos that knows it is still spinning.